Hi everyone, welcome back. So in this video we're going to apply some of what we know about local stability in first order equations to the simple example of population growth, which is a nice single variable system where you're mostly interested in just, well, how big is the population at some point in time. And some of this will seem very familiar when you compare it to the population growth stuff we did back in the difference equation section, but there will be a couple of subtle differences. So let's go ahead and get started. And the first thing we're going to start with is simple exponential growth. So when we're talking about population models, we actually give this a slightly different name. So this is, let me get my lines here. This is actually known as Malthusian growth, after Thomas Malthus, who was an English economist who was studying the theory of population explosion. So Malthusian growth. And that basically just has a single idea. So the rate of growth is proportional to population size. Population size. Okay, so that's pretty easy, right? So let's let A equal to B minus D be the birth rate minus death rate. And so A here is our proportionality factor. Okay, so once we have that, well, we want the rate of growth, which is just x dot. So that's x dot, or dx dt. Well, we want that to be equal to a times x. And this is some function f of x. So this is in many ways, the simplest possible non-trivial differential equation. And we know how to solve this. So x of t is equal to the initial value, x naught, times e to the a x. And so we also know that we can find equilibria, right? So if we were trying to find equilibria of the system, well, what we want is some x bar such that x dot is equal to 0. So we're going to assume that a is not equal to 0. A is not equal to 0, because otherwise it's not interesting. So if a is not equal to 0, then 0 equal x dot, what you want is the rate of change to be 0, so you have ax is equal to 0, which implies that ax bar is equal to 0, which implies that x bar is equal to 0, is the only equilibrium. Is this stable? Well, that's pretty easy, right? So note that f prime of x is equal to a, it's just a constant since this is linear. So f prime of 0 is also equal to a. So 0 is locally asymptotically stable if a is less than 0 and is unstable if a is greater than 0. And of course, since this is something we can solve explicitly, we can graph this out. So what it looks like is if we have our t-axis here and we have our x-axis here, well, you end up with an exponential growth here if a is greater than 0, and if a is less than 0, you start out some here and then you decay down to 0. So a is less than 0. Okay, so that was a super simple example. Let's move on now to a slightly less trivial example of logistic growth. So you'll recall when we talked about difference equations that we did also talk about logistic growth, but that it had some weird chaotic behavior for some parameter ranges where it jumped all over the place. Luckily, it turns out that when we're talking about differential equations, that doesn't really happen because you can't jump back and forth, and so you don't have the same kind of chaotic behavior for logistic growth in differential equations that you do with the difference equations. But let's go ahead and define this. So this was introduced by Pierre Verhulst. So we don't call this Verhulstian growth, though we sometimes do refer to the equation as Verhulst's equation. Just like we refer to, sometimes in population studies, we refer to exponential growth as Malthusian growth. And this was also, let's say this was 1837. So this was a while ago. And what we are assuming now is that the rate of growth is a decreasing function of population size. So let's say rate of growth. Let's call that a variable a. So a of x. So we're going to say that the rate of growth, a, is a function of the population size x is equal to r times 1 minus x over k. So what does this mean? So this means that for population sizes bigger than, therefore, for x greater than, I seem to have, that's a mistake, sorry, I put the fraction wrong. So 1 minus x over k. So for populations x greater than k, not 5, don't know why I wrote that there, greater than k, the rate is negative. So here k is something we call the carrying capacity, because that's the maximum number that the system supports in a stable way. So if the population size is greater than k, then the rate is negative, and for populations x less than k, the rate is positive. So things grow when you have less than k, and things decrease if you have more than k. So this is our rate of growth, and let's write out our differential equation. So again, we have x dot is equal to ax, but here a is a function of x. So we have a of x times x, which is equal to r times 1 minus x over k times x. So this is again an autonomous equation, but this here is autonomous nonlinear equation. So given this autonomous nonlinear equation, we can still solve for equilibria. So in order to solve for equilibria, we need to set x dot equal to 0. So if 0 is equal to r times 1 minus x over k x, well, this implies, since it's already in factored form, that x is equal to 0, x bar. X bar is equal to 0 or k. So these are the only two equilibria. And we can also directly solve this differential equation. And let's go ahead and do that, just so that we see what goes on here. Let's see, just a moment. Actually, let's go ahead and try to analyze the stability of these equilibria first. So in order to do that, we have f of x is equal to r times 1 minus x over k times x. So what's f prime of x? Well, you use the product rule. So r is equal to, f prime of x is equal to r times the quantity 1 minus x over k times the derivative of x, which is just 1, plus x times the derivative of 1 minus x over k, which is minus 1 over k, which is equal to r times 1 minus 2x over k. Okay, so then we know that f prime of 0 is equal to r, it's just equal to r, and f prime of k, well, when we plug in k into that, you end up with 2k over k, which is minus 2, so that's minus r. So if r is greater than 0, then 0 is an unstable equilibrium, locally at least. I mean, it's unstable, period. And then k is a locally stable, asymptotically stable equilibrium. Okay, so this is only talking about local stability. It turns out that for this equation, we can't actually explicitly solve it, and so you can solve it using separation of variables, so just standard differential equation techniques. It turns out that if we solve using separation of variables, then we get that x of t is equal to x naught times k over x naught plus k minus x naught e to the minus rt, where x naught is equal to x of 0, of course. And so it turns out that this implies that the limit as t goes to infinity of x of t is equal to k if x naught is greater than 0 and r is greater than 0. So k is actually globally asymptotically stable. So all the solutions, if r is greater than 0 and your initial starting point is greater than 0, then you will go to the carrying capacity k, even if you start below or above. And so this is a nice sort of result because it means that if you have, let me draw this out. The basic idea here is you have some carrying capacity, so this carrying capacity k, and that no matter where you start, if you start down here, you might start out with exponential growth, but then it levels out as you get closer to the equilibrium, or as you get closer to the carrying capacity. And you might end up with something similar over here. And if you start above, well, the same thing happens. So then you exponentially decay towards that equilibrium. So let's say this is x of t, and this is time. So for various initial conditions, you always go to the carrying capacity. Obviously, if you start at 0, well, then that is an equilibrium, so you just stay at 0, but it's an unstable equilibrium, so even if you're slightly off from 0, you end up going to k, assuming you're positive, since we're only going to talk about positive values since we're talking about populations. Okay, so those are two of the simple models of growth that correspond, roughly speaking, to things you've seen before in difference equations, though they have slight quirks on them because differential equations do have different behavior on certain timescales than difference equations do. But it turns out that there are some other effects that can happen with real population models. So these are very simple population models, and we're going to introduce a new effect, which we're going to call the alley effect, which was named for a zoologist, Werner Alley, who studied these things in 1931. And so it turns out that often there's reduced fitness for low population sizes. So if you have a really, really small population, often your reproduction rate is actually lower than that of a somewhat larger population. There are a couple ways you can think about this. One of them is if you have a really, really low population density in a really big area, well, it might be hard for animals to find mates. And so that actually reduces the overall fitness of the population because you're not, the animals aren't reproducing at the same rate as if they were a bit more densely clustered. And so another way of thinking about it is sometimes if you have a really, really small population size, you might not have a sufficiently broad genetic pool in order to have the highest fitness for the species as a whole. And so this is an effect that people discovered empirically. And of course, if you're a mathematical biologist, you want to model this effect. So one of the ways you do this is you model a minimum viable size. So you model a threshold below which the population tends to die out to extinction. So let's say, again, we're going to think about reproductive rate. So one model, say that a of x, of course this is the reproductive rate, and x is the population size. Let's say that that's equal to a1 plus a2x plus a3x squared. And so note that above in our logistic model, we had a of x is equal to r times 1 minus x over r. Here, which was, here we have a quadratic function. So this is a quadratic function. So this is a quadratic function in your population size. And so as your populations get bigger, that the actual size of your population does have an effect, and that effect is magnified when you're bigger. Or the A3 term is magnified when you're bigger. So then what do we get? So then we have x dot is equal to ax per usual, but here a is equal to this quadratic function. So then that's x times a1 plus a2x plus a3x squared. Okay, and we often set the parameters where, let's say, a1 is less than 0, a2 is greater than 0, and a3 is less than 0. Okay, so now what happens when we do that? Well, the first thing we want to do is, of course, we want to solve for equilibria again. So in order to solve for equilibria, we get 0 is equal to x times a1 plus a2x plus a3x squared. And we're going to assume that we can factor this out. 0 is equal to x times, well, this is a quadratic equation. You can apply the quadratic formula to factor it out. Let's assume that we've already factored it out. So this is going to be 0 is equal to a3x and x minus, let's call this alpha 1, and x minus alpha 2. So where the alphas are the solution to the quadratic equation. So where alpha 1 and 2 is equal to minus b. Yeah, so I'm not actually going to solve it because you end up with a lot of coefficients, but you just apply the quadratic equation and you can solve for alpha and the roots, quadratic equation. Okay, so then we have these, and let's go ahead and order these. So x is equal to 0, alpha 1, and alpha 2. And without loss of generality, we're going to say that 0 is less than alpha 1 is less than alpha 2. So the solid has 3 different equilibria. And, well, what are these? When are these stable and when are these unstable? Well, in order to figure that out, we just need to take the derivative, use the derivative test, right? So what we can do is f of x is equal to x times a1 plus a2x. Actually, let's do this derivative test with, in the version a3x times x minus alpha 1, x minus alpha 2. So then f prime of x is going to be equal to a3 times the quantity x minus alpha 2x plus x minus alpha 1x plus x minus alpha 1 x minus alpha 2. Okay, and so f prime of 0 turns out to be equal to a3 times minus alpha 1 times minus alpha 2, which is less than 0. So x bar equal to 0 is locally asymptotically stable. And well, let's see, what is f prime of alpha 1? So our smaller of our 2 equilibria. Well, when you plug this in, you get that f prime of alpha 1 is equal to a3 times alpha 1 minus alpha 2 times alpha 1, which is greater than 0 because Wait a moment. Is that right? F prime of alpha 1 is equal to alpha 1 minus alpha 2. Oh, yeah, sorry, that is correct. So that is greater than 0 because note that, where was it? A3 is less than 0, which is important here. So A3 is less than 0, and so basically sorry, I should go back and explain a little bit what these different constants mean. So A3 being less than 0 means that when you have a lot of when your term is really, really big, when your population is super big, then it tends to the rate is negative and it tends to get smaller. So this is the same sort of effect as you get with the sort of carrying capacity, except we've encoded it into a slightly different term. And A1 being less than 0 basically means that if your population is too small, it also decreases. Whereas A2 being greater than 0 means that there's some intermediate sizes which the population does increase. Okay, but anyway, here we've solved for this, and we get that the alpha 1 equilibrium is unstable. So x bar is equal to alpha 1 is unstable. And lastly, f prime of alpha 2. Well, when we solve for that, you end up getting A3, which is negative, times alpha 2 minus alpha 1 times alpha 2, which is less than 0. So x bar equal to alpha 2 is locally asymptotically stable. Okay, and you can explicitly, so this equation turns out to be one that you can explicitly solve, but it is a little bit tricky. However, even without solving the actual differential equation here, by using this local stability analysis, we know that we have 3 equilibria, and 2 of them are stable. So if your population is too small, you'll go down to 0. If your population is too big, you'll go down to your... if your population is too big, you go down to some other equilibrium. But if your population is in the middle, then it goes up to this carrying capacity. And so this is what you can do with this sort of local stability analysis for the simple example of population growth. And in the next couple lectures, we'll be talking about extending this to more complicated nonlinear differential equation models. So I will see you in class.